Welcome to the latest video in your Design of Experiments course. Now in this video we move on to exercise 4, and of course what we're going to do is repeat the exact exercise that we've just completed. So what we've now got for you is another 6-factor. It's a 6-factor experiment. Of course, because we have 6 factors, if we look at the computer-aided menu in DOE Pro, what are we going to see? Well, we're going to see the recommendation for 6 factors is that you start off with an L12 screen. So we are repeating the exact experiment that you've just done. Obviously it's a different system, a different 6 factors and a different target. L12, you're going to do the marginal means. And of course, as you do the marginal means, you do an analysis for S, you do an analysis for Y. S is that you identify a factor to minimize standard deviation. Y, you pick the 3 biggest signals. And of course, what do we do next? We put those 2 pieces of knowledge into a full factorial. Now, just something to say on this exercise. When you go and look for the 3 biggest signals, actually in the marginal means plot, really there's only 2 big signals. But I'm trying to keep this consistent for you, so I'm saying 3 each time. I'm effectively saying to you, let's go do a test and let's go and create a 3-dimensional box. And I'm keeping it to 3 just to be consistent. In real life, would I stick at 3? No, not necessarily. I might just pick the 2 big signals in this case, because those 2 big signals bully the process. They push the process around. But for consistency, I'm telling you to pick 3. So you have 2 files. One file is called temperature 1. Temperature 1 contains the L12 for you to analyze, and the full factorial is contained in temperature 2. The full factorial, of course, we go and model the y hat, and then we ask it to hit the target. Now the target in this case is a temperature target, and the temperature target is 650 degrees. So that's what we're trying to hit. Now, of course, because you've already done this once, this should be something that you can just follow through and do again without my help. So at this point, go and open temperature 1, do the L12, go and open temperature 2, do the modeling, and then come back with a suggested optimized set of values. So if you want to stop the video now, you can do that. If you're not sure and you want to watch my analysis, I'm about to do the analysis now. And one last thing, by the way, when you do the optimization down here, this particular exercise, the target is actually well inside the box. Previous exercises we've done, the target has been at or near a corner point. And so we've all arrived at the same values, the same optimized values. Because we're in the middle here, your optimized values and my optimized values could be very different. That's okay. I think the main thing is check that the model, as long as your model is the same as mine, then the optimizer is going to be working perfectly well. As long as you've asked it to be equals to 650 degrees, the optimizer is going to be working perfectly well. So that's going to be the test on this exercise rather than you agree with me on the screen. So if you want to stop now, do the analysis, fantastic. If you want to stick with me, let's go to the computer. Okay, so here we are, look, with the explanation of the 6 factors. So we're trying to control the temperature as an output to this process. We have 6 factors: milligrams of beryllium, 20 milligrams all the way up to 80 milligrams, oxygen ratio 1 to 10, nitrogen level 20 to 500, ionization rate 5 to 10, water source 1 or 2, and the sodium content there at the end 0.1 to 0.9. We've run a capability study, and the capability study is sitting at the end there. You can see that we are hitting approximately a temperature of 600. So we're sitting actually on the bottom tolerance. We're trying to hit 650, and the tolerances are 600 at the bottom, 700 at the top there. We're sitting right on bottom tolerance, which means that pretty much approximately 50% of everything we produce is defective currently. So that's the current setup. Now, because it's 6 factors, of course, we go into the L12. So let's go to the L12 first and do the graphical marginal means analysis. So here we are in the L12, sigma zone, analyze design, marginal means plot, both the Y and the S. Okay, so on the S marginal means, of course, we're looking for the biggest signal. The biggest signal is coming from that big brown line, nitrogen level. We want to be at the bottom of that line, and in order to do that, we're going to have to go down here to a setting of 200. So there is our S hat knowledge with the first marginal means plot. That's the first piece of knowledge. Let's put that on the whiteboard. Okay, so in order to control S, where are we going? So our fix here, nitrogen is going to 200. That's the first piece of knowledge that we've gained from the L12. And it's as simple as that. I mean, really, 12 tests, simple graphical analysis, great piece of knowledge. Now let's go and look at the 3 biggest signals. As I said, it could just be 2, but let's take a look at them now. Okay, so here's the marginal means. First of all, of course, take a look at the nitrogen level. So the nitrogen level with regards to moving the mean in this process is not doing anything at all. So putting nitrogen to 200 is no risk at all. And then, of course, you can see the 3 biggest signals. So the 3 biggest signals are the 3 on the right. We've got the ionization rate, which is clearly having the biggest effect. You know, we're moving all the way from 350 there at the bottom, all the way to 650 at the top. We've then got the water source, and then we've got the sodium content, the NaCl. Now, as I said to you, it is possible that you could just take ionization rate and NaCl across into a 2 to the 4 full factorial. The water source is only just slightly bigger than the oxygen ratio. And there is an argument that says, well, if you're going to take the water source, why don't you take the oxygen ratio with it? Now again, if one of those is cheap, one of those is more expensive, that would help you to make a decision. It could be that if oxygen ratio is cheaper than the water source, that we may take the oxygen ratio instead, or we could take it as well. This is about wisdom. I can't put all the practical elements on the table with each of these exercises, but you would use your wisdom and you would decide which factors you want to take into the modeling DOE. So there are the 3 variables: ionization, water source, sodium. Let's put those 3 on the board. Okay, so those three go on the board. Here we go. Ionization, water, and NaCl. So they're the three that we're going to model. And if we go to the full factorial now, temperature 2 will contain these three. What will we do? We will model Y only. This is a modeling DOE, remember. We will model Y only, and then we will ask the optimizer to hit 650, and then of course we'll do the confirmation test. So let's go back, open up the full factorial and do the modeling. So here we are with the full factorial. Analyze design, regression. No need to do the marginal means, of course, because the marginal means were done in the L12. So we just go straight to modeling. Here's the model. You can see the p-values. We got some high p-values. So the two ways have all got to come out. So all of the two ways can be lost. They're the only interaction decisions I'm going to make. So I'm going to regress that first. And then I'm going to make decisions about my main effects last. Now, in this case, look, I've got an ABC three-way interaction. So because I've got a three-way interaction, I'm going to leave A in, I'm going to leave B in, and I'm going to leave C in. Even though B has a very high p-value and it shouldn't really be there. You can see though, look at the coefficient, 0.73 of a degree centigrade. It's making very little difference anyway, so it's not going to cause a problem for us. R squared, by the way, look, 0.99, you know, very high. I wouldn't expect you to see these numbers in real life. If you're over 0.8 in real life, you're doing very well. To get 99%, this probably relates to the type of exercise that we're doing. So there's the model. And now, of course, what I'm going to do is go to the optimizer. Multiple response optimizer. Are any of these not continuous? Water source isn't continuous, so I need to take that check mark away. Click OK. Click through the window that we don't use. And then I'm going to say equals to 650. Add the objective and optimize. And it says at the top, it says, yes, I can hit 650 with settings of 5.18, water source of 2, and a sodium content of 0.62. Now, as I said to you, you probably get different results to this. If I hit optimize again, so watch this. If I hit optimize again, watch those three values change. So now it's gone 5.23, water source 1 this time, water source 1 and a sodium content of 0.64. So it's given me a different optimized set of settings. You might be seeing that. The computer has freedom to do that within the model. So that's perfectly okay. I'm going to put those settings to worksheet. They say that I'm going to hit 650. So there are my settings, 5.23, water source 1 and 0.64 on the sodium. There's my optimized settings. Let's put those on the board and then we'll come back and do a confirmation test. Okay, so the 3 was 523, water source 1 and 0.64 for the sodium. So there are my optimized settings. It says that I'm going to hit 650 exactly. Just one point, by the way, before I move on, that's worth repeating. The knowledge that I gained here, let's put a different color on the board. The the knowledge that I gained here for S, nitrogen to 200. Before I ran the full factorial, I dialed that into the system. So my full factorial was ran with the minimum amount of error appearing in the data, the minimum amount of standard deviation. That's partly why my R squared was 0.99, because I dialed all the error out, I dialed all the noise out. And that's very important. You're not doing these experiments, you're just analysing the data that I'm giving you. I'm showing you how to do the analysis. But in real life, you need to tune into this wisdom and you need to behave like this. Do an L12, get knowledge, take the knowledge back to the system, run a second experiment with standard deviation minimized and the three biggest signals sitting in your full factorial, and then model for Y. You need to get comfortable doing this in a real situation, not just the exercises that I'm giving you. So now we've got these values here. Prediction, by the way, is 650. That's what it says I'm going to hit. Let's go to the CPK screen. Let's run the original performance and let's see how our process behaves with our new optimized settings installed. Okay, so here's the original setup. So I haven't adjusted it at all. I'm going to go to the CPK view and I'm just going to say, here's what the process is originally doing. So this is like the picture that we looked at with approximately a 50% defect rate. And you can see that the results as well are quite wide. They won't fit inside the tolerance. If I centered that process, we won't fit inside the tolerances as currently set. Let's save that, take a picture, remove the data and generate a fresh data set of 100 samples. Whoops, didn't change the settings. Let's do that again. So I'm going to go nitrogen to 200, ionization rate at 523, so that's come down. I can only do 5.2. I need to go water source 1 and I need to go sodium content to 0.64. Let's take that up. 0.64. So there are the settings. Let's get rid of that data. Generate 100. So the prediction was we'd hit 650. We've hit 646.8. You can see that we've dialed the standard deviation right down and we're inside the target and everything's right with the world. So just to point out, we squeezed in the shape of those results by fixing nitrogen to 200. Then what we did, we ran the modeling DOE to place that new distribution on our target. They're the two techniques that you're using in design of experiments. How to minimize standard deviation and how to put the average, how to put the mean on target. And there's our optimized results right there. Okay, it's as easy as that. We've been at this video for about 15 minutes and we've already got results. Now just something to say, we haven't multiplied the combinations up, but if you take a look at the choices that we have, things like we have 300 choices for nitrogen. I think we have 600 choices for the first variable as well. We have 2 water sources. We have the sodium content from 0.1 to 0.9. If you multiply those choices through, I think what you get is 128 billion ways of setting this process up. That's what was sitting in front of you. That's what the challenge was. And in order to gain process knowledge and solve the problem, you ran 2 experiments. 48 data points in the first experiment, the L12. 40 data points in the second experiment, the full factorial. So top that up, what have we got there? 88. For 88 data points, you've interrogated this design space. And inside 15 minutes, you've come up with optimized values. What did we say we hit? So 650 was the prediction. We hit 646. Works pretty well. I'll say it again. How else could you do this? Nobody, if you're working inside a company and you have systems that are as complex as this, and by the way, you have systems that are more complex than this, how else would you answer this problem? Now, what we're going to do in the next video, we're going to take a look at exactly this type of problem. Screening first and modeling. We're just going to give you a little case study. It's an injection molding machine. And what you'll see is not 128 billion choices. You'll actually see 1.4 quadrillion choices. Again, how do we solve the problem? L12 followed by a full factorial. So we're going to have a look at that case study in the next video. See you next time out.